People love to watch science fiction movies where a group of heroic astronauts climb into a shiny rocket ship, blast off to Mars, walk around on the red sand, do a couple of science experiments, and then hop back into their ship, push a big red button, and effortlessly fly back home to Earth in time for dinner. It looks so easy on screen, doesn't it? You see the little spaceship land on Mars, you see it blast off again, and you think, well, if we can build a rocket big enough to get there, why wouldn't we be able to just build another rocket to bring them back? When you look at the actual physics, when you sit down with a piece of paper, a pencil, and the cold, hard, uncompromising laws of gravity, thermodynamics, and orbital mechanics, you realize that sending a human being to Mars is only half the problem, the easy half. The idea that we are going to send people to Mars and then just swing by and pick them up a few months later is one of the most absurd, ridiculous illusions modern pop culture has ever created. If you go to Mars, for all practical purposes and for a very, very long time, you are staying on Mars. You aren't coming back. To understand why a return trip from Mars is almost physically impossible with the technology we have today, or even the technology we're going to have for decades, you have to start with something very simple that most people completely take for granted: the weight of fuel. Imagine you want to drive a car across the country. You fill up your gas tank with 20 gallons of gasoline. The gas weighs a couple 100 pounds, your car weighs 2 tons, and you drive down the highway. If you need more gas, you stop at a gas station. But what if there were no gas stations on the entire continent? You'd have to carry all the gas you'll ever need for the whole trip right inside your car. But wait, the more gas you put in the trunk, the heavier the car gets. And the heavier the car gets, the more gas you need just to haul the weight of the extra gas. This is what rocket scientists call the tyranny of the rocket equation, formulated by a brilliant Russian named Konstantin Tsiolkovsky. It isn't a rule made up by NASA. It is a fundamental consequence of Newton's third law of motion. For every action, there is an equal and opposite reaction. To push a rocket forward in the vacuum of space, you have to throw hot gas out the back as fast as you possibly can. The momentum of the gas going backward equals the momentum of the rocket going forward. Now, think about what it takes to leave Earth. Earth is a big, heavy rock. It has a tremendous gravitational pull. To escape Earth's gravity well and head toward Mars, you have to reach what we call escape velocity, which is about 25,000 miles per hour. To get a tiny capsule weighing a few tons up to 25,000 miles per hour, you need a giant Saturn V or Starship rocket that weighs millions of pounds. Over 90% of the mass sitting on the launch pad isn't the astronauts, it isn't their food, and it isn't their science equipment. Over 90% of that giant tower is pure, heavy liquid fuel and oxidizer just to push that tiny little nose cone out of Earth's atmosphere. So let's do some basic math. You launch off Earth. You use up 90% of your rocket just getting into space. Now you're coasting through the void toward Mars. You arrive at Mars. You can't just land instantly, because if you hit the Martian atmosphere at 20,000 miles an hour without slowing down, you turn into a glowing streak of plasma and vaporize instantly. So you have to use a combination of heat shields, giant parachutes, and retro rockets, which burn fuel, to slow yourself down and land gently on the surface. Now you're sitting on Mars. You've made history. You step out, take your photos, plant a flag, and look at the rusty horizon. Beautiful. Now you want to go home. How do you get back? You have to climb into a rocket, accelerate up to Mars's escape velocity, which is lower than Earth's, but still a staggering 11,000 miles per hour. Blast off into orbit, line up your trajectory with Earth, and fly back across millions of miles of empty space. Where did the rocket sitting on Mars come from? Where did the thousands of tons of fuel needed to push you off Mars come from? Did you haul that rocket and all that fuel all the way from Earth? Think about the hilarious compounding nature of the rocket equation. If you want to carry fuel to Mars so that you can burn it to leave Mars later, you have to carry the weight of that future fuel all the way off Earth. That means your initial rocket sitting on Earth can't just be 90% fuel. It has to be 99.99% fuel. You would need a rocket the size of a skyscraper just to land a tin can on Mars that has enough gas left over to hop off the surface. Scientists look at that math and say, okay, carrying all your return fuel from Earth is completely insane. It's physically impractical. So what's the clever alternative people talk about? They say, we will manufacture the fuel on Mars. That sounds wonderfully high-tech and futuristic, doesn't it? You send a robotic factory ahead of time, it scoops up Martian soil, extracts ice water, sucks carbon dioxide out of the thin Martian air, uses a nuclear reactor or acres of solar panels to run electrolysis and chemical reactions, and produces liquid methane and liquid oxygen. You fill up the return rocket's tanks right there on the red planet. It's a magnificent chemical engineering concept on paper. Sabatier reactions, Fischer-Tropsch synthesis. We know the chemistry works in a warm, clean laboratory on Earth where you have a team of 50 technicians in white coats standing by with wrenches and laptops. But now, put that chemical factory on Mars. Mars is not a pleasant, sunny vacation spot. Mars is a hyper-arid, frozen desert where the average temperature is 60 degrees below 0 Celsius. The atmosphere is less than 1% as thick as Earth's, so thin that liquid water instantly boils away into vapor. The soil is full of toxic, abrasive perchlorate salts that corrode metals and destroy machinery, and every few years, giant global dust storms sweep across the entire planet, blocking out the sun for months at a time, coating every surface in fine, electrostatically charged red grit that clogs gears, coats solar panels, and short-circuits electronics. Now imagine sending an automated, hyper-complex chemical refining plant to Mars, landing it blindly on the rocks, and expecting it to autonomously drill through frozen soil, harvest tons of water ice, pump toxic gases, compress them at extreme cryogenic temperatures, and store thousands of gallons of explosive rocket propellant without a single human being around to fix a jammed valve, clear a dust filter, or tighten a loose screw. If a single rubber seal degrades in the extreme cold, if a pump motor gets jammed by fine Martian dust, or if a solar array fails to deploy, the fuel factory stops. And if the fuel factory stops, your astronauts sitting on Earth watching the telemetry realize something terrifying. Their ride home was never built. Let's assume, for the sake of argument, that by some absolute miracle of engineering, the fuel factory works perfectly. It sits on Mars for 2 years, quietly humming away, and fills up a shiny rocket with tons of liquid methane and liquid oxygen. You launch your astronauts from Earth, they land on Mars next to the fully fueled rocket, spend a few months exploring, get into the return ship, and prepare to blast off. Are you home free? Not even close. Now you run into the second brutal law of the universe. Orbital geometry and timing. Earth and Mars aren't sitting still in space, side by side like two houses on a suburban street. They are both orbiting the sun at different speeds and at different distances. Earth is on the inside track, zipping around the sun in 365 days. Mars is on the outside track, taking nearly 2 Earth years, 687 days, to make a single orbit. Because they are moving at different speeds, the distance between Earth and Mars is constantly changing. Sometimes they are on the same side of the sun, relatively close together, a mere 35 to 50 million miles apart. Other times, Earth is on one side of the sun, and Mars is on the exact opposite side, separated by 250 million miles of space. You cannot just point a rocket at Earth and hit the gas whenever you feel like it. You can only launch between Earth and Mars when the two planets line up in a very specific, narrow planetary configuration. We call this an orbital launch window. And this launch window only opens once every 26 months. Think about what that means for human biology and psychology. If you land on Mars, you cannot say, "Gee, I'm feeling sick, my spacesuit is leaking, or I miss my family, let's head home next week." You can't leave. You are physically trapped on the surface for roughly 500 days. Over a year and a half. Just waiting for the planets to swing back into position so that the laws of physics allow a return trajectory. What are those humans doing during those 500 days? They aren't sitting in an air-conditioned hotel. They are living inside a cramped, pressurized tin can, subjected to environmental conditions that are actively trying to kill them every single second of every single day. Let's look at what the Martian environment does to a human body over a year and a half. First, radiation. Earth has two incredible invisible shields that protect us from the cosmic horror of deep space. A thick atmosphere that absorbs high-energy rays, and a powerful global magnetic field generated by our molten iron core that deflects charged particles coming from the sun. Mars has neither. Mars lost its magnetic field billions of years ago, and its atmosphere was stripped away by the solar wind. On Mars, you are bombarded constantly by two deadly sources of radiation. First, solar particle events, giant, unpredictable belches of high-energy protons spewed out by the sun during solar flares. Second, galactic cosmic rays, super high-energy particles originating from exploding stars outside our solar system, traveling at near the speed of light. Cosmic rays aren't like X-rays at the dentist's office where you put on a lead apron. Cosmic rays are so energetic that when they hit the metal walls of a spaceship or a Martian habitat, they shatter the atoms of the wall itself, creating a secondary spray of subatomic shrapnel called secondary radiation. Passing through a human body, these high-energy particles act like microscopic bullets, ripping through cell membranes, shredding double-stranded DNA, and causing severe, irreversible genetic damage. Over a 500-day stay on Mars, astronauts would absorb radiation doses that dramatically elevate their risk of fatal cancers, cause cognitive degradation in the brain, and destroy their immune systems. To shield against this radiation, you can't just wear a heavy suit. You need meters of solid rock or lead. The only way human beings can survive on Mars for 500 days without getting cooked by cosmic radiation is to dig deep underground, piling tons of Martian dirt on top of their habitat, living like subterranean moles in dark, buried bunkers. Second, gravity. Earth's gravity is 1 g. That's what our bones, muscles, heart, and blood vessels evolved to handle over 3 billion years. Mars's gravity is only 38% of Earth's. Roughly 1/3. When you place a human body in 1/3 gravity for a year and a half, the body immediately realizes it doesn't need all that heavy skeleton and muscle mass anymore. Why keep dense, heavy bones when you don't need to support your full weight? Your body starts reabsorbing calcium from your bones, dumping it into your bloodstream and urine, causing your bone density to plunge by 1 to 2% every single month. Your leg muscles atrophy. Your heart muscle shrinks because it doesn't have to work as hard to pump blood up to your brain, and the valves in your veins lose their elasticity. By the time those 500 days are up and the launch window finally opens, your astronauts aren't pristine athletic superheroes. Their bones are brittle like glass, their hearts are weakened, their immune systems are compromised by radiation, and their vision is distorted because fluid shifts in low gravity push against the backs of their eyeballs. And now, in that physically degraded state, you expect them to climb into a return rocket, buckle themselves into a chair, pull 6 or 7 Gs of brutal acceleration during launch off Mars, endure another 8 months of zero-gravity deep space flight back to Earth, and then slam into Earth's thick atmosphere, pulling another 10 Gs of deceleration. When they touch down on Earth, their fragile, calcium-depleted bones would shatter under normal Earth gravity. They wouldn't be able to stand up, walk, or even breathe properly without their weakened chest muscles collapsing. And we haven't even talked about the psychological aspect. Put 3 or 4 human beings inside a small pressurized habitat buried under red dirt for 2 years. They are drinking recycled urine, eating rehydrated paste, looking out a tiny window at a barren, toxic landscape where nothing moves except the dust. Earth is just a tiny, invisible blue speck lost in the night sky. The delay in radio communications between Earth and Mars is up to 20 minutes each way if you say, "Houston, we have a problem." It takes 20 minutes for your voice to travel to Earth at the speed of light, and another 20 minutes for Houston's response to travel back. You cannot have a real-time conversation. You are completely, terrifyingly alone. If a technical failure occurs, no one on Earth can save you. No supply ship can be rushed to your aid. If you run out of oxygen, water, or food, you sit there in the dark and watch the clock tick down. The sheer psychological pressure of that absolute isolation is something no human mind in history has